From lasers to surgical endoscopes, glass is an essential building block in optics and imaging. This unique combination of transparency, refractive properties, and the ability to be formed into precise geometries has made it a mainstay in the evolution of technologies that extend human vision and awareness of the universe. From the creation of rudimentary lenses to the production of elaborate optical systems, glass have paved the way for advancement in science, communication, and medicine alike. Light interacts with glass by refractive, and dispersive properties. Hence the role of glass in optical devices, which is lenses, prisms, and mirrors. Additionally, innovation in glass manufacturing have birthed specialized grades such as optical glass, fused silica, and photonic glass, each finely tuned to meet precise demands for imaging systems and optical networks. Such innovations have driven progress in areas such as microscopy, photography, astronomy, and telecommunications. Glass is essential for optics and imaging, as we explore in this case study from its physical properties and technological uses to the industry's pleasures. Also, the work hopes to underscore the importance of glass in modern optical science and in engineering through an exploration of glass characteristics as well as usefulness.
Next, topic overview. First, glass play a crucial role in optics and imaging due to its ability to transmit, refract, and focus light diffraction. Second, its influences present in optical fibers, glass revolution, photography, microscopy, and medical imaging. Third, glass is indispensable in its application from consumer electronic to scientific instruments and healthcare technologies.
Glass was made from the combination of lead and alkali oxide and lime and heated to 2400 until 2700 degrees Fahrenheit. Archaeologists found yet it was produced by the Mesopotamians around 4000 to 5000 years ago. One of the famous examples is Nimrud lenses that was made by the ancient Assyrians between 750 and 710 before century. It was used as a fire testing instrument and magnifying glass. Last but not least, one of our scientists, Ugo Scott, developed glasses which reproduce the characteristics, revolutionizing technical and optical mechanical glasses. This enabled significant scientific and technological advances.
Next, let's talk about application of glass in optic and imaging. There are three examples. The first one is microscope lenses, second, medical imaging, and the third one is a mirror. So the first application is microscope lenses. It is a specialized lens used in a microscope to magnify small objects, allowing detailed observation of minute structure by bending light rays and also focusing them onto the viewer's eye or camera sensor. So there are two components of a microscope, which is the first one is objective lens, and also the second one is eyepiece, or we call it ocular lens. So application of a microscope lens in real life is for biological research, medical diagnostic, material science, and also industrial inspection. Next is medical imaging. Medical imaging is the use of light to create image of internal body structure for diagnostic purpose. There are applications in real life for a medical imaging, which is for ophthalmology, gastroenterology, oncology, and also wound monitoring. And there are also example for medical imaging, which is the first one is optical coherence tomography, second is confocal microscopy, third is fluorescent imaging, and the last one is for diffuse refracting imaging. And also the last application of glass in optic and imaging is mirror. Mirror is a precisely manufactured surface designed to reflect light, allowing for the manipulation of light beams by redirecting, focusing, or collecting them. There are three types of mirror, which is, as we know, the first one is plane mirror, second one is concave mirror, and the last one is convex mirror. Application of mirror in real life is for astronomy, lasers, medical imaging, and also the last one is optical instrument.
Hi, my name is Kaisa, and I will be presenting about the examples of glasses in optic and imaging. For the first example, it was example of glasses in optic, which is optical lens. Optical lens is a transparent piece of glass that was specifically crafted to gather and direct light rays from an object. It concentrates the light in a way that forms a clear and focused image of that object. One of the challenges in making optical lens is correcting the optical aberrations. These flaws can alter the image created by the lens, diminishing its precision and overall effectiveness. One of the ways to overcome the challenge in order to help in minimize distortion, create sharp and clear image is by using geometrical method. Geometrical method is a method in understanding how light moves through lenses and optical system. Next is by using ray tracing method. Ray tracing method is a more detailed method from the geometrical one. It's a computer graphics method that models the behavior of light within a scene by following the trajectories of individual light rays. For examples, how light bends when it enters different materials or uses the refractive indices to figure out how light travels and so on. Next is the examples of glass in imaging. The most well-known one is the MRI scan. MRI, which is known as magnetic resonance imaging, is a scanning technique that employs powerful magnetic fields and radio waves to generate detailed images of the body's internal structures. One of the challenges in the making of MRI scan is to obtain the perfect magnetic shielding. It's essential in MRI design since it's confined the machine's strong magnetic fields. Hence, it prevents external interference to ensure safety and no disruption to the performance of the machine. The ways to overcome this challenge is by using advanced shielding materials. For examples, using the high-performance alloy, it is highly effective in redirecting magnetic field, or by using hybrid materials which can enhance shielding effectiveness while minimize the cost. Next is by improving the room design so that we can control the magnetic fields for safety. We need to make sure the walls, the floors, and ceilings contain fringe fields. Next, the advances and innovation of glasses in optic and imaging. First, the advanced glass composition. From FISBA 2024, they stated that through meticulous atomic level engineering, novel glass compositions have emerged with unprecedented optical properties. This material exhibit minimal dispersion and high refractive indices, enabling superior light bending and focusing for sharper, more accurate imaging. Second is the chalcogenide glass. Chalcogenide glass is a specialized glass composed of chalcogen elements such as sulfur, selenium, or tellurium combined with metals or semi-metals. From CREOL, the College of Optics and Photonics 2015, they stated that in glass, CHG-based optical materials that transmit throughout the infrared IR have seen increasing use in a diverse range of infrared optical systems.
There are so many benefits and advantages of glass in our daily life, which is the first one is to enhance image quality. The glass has the ability to reduce distortion because glass improves the precision and sharpness of image, whether in cameras, telescope, and also medical imaging. So the second one is long-term application. Glass can be used in long-term because it has chemically stable, resistant to corrosion, and also can withstand extreme environmental conditions such as high temperature and also pressure. And the last one is for scientific and industrial advancement. The use of glass in optics has propelled discoveries in astronomy, medicine, and material science, enhancing both research and also practical application.
Manufacturing glasses involves several challenges that need to be addressed to ensure quality and performance. One major issue reduce clarity, create glare, or impact the durability of the lenses. Another challenge is material limits here, as certain materials may lack the strength, flexibility, or other properties required for advanced applications. Here are some solutions for the issue. The first one is coating technology. Coating enhances optical performance by reducing reflection, increasing durability, and improving light penetration. They are crucial in devices like cameras, glasses, and industrial optics. The next one is innovation in lens design. New lenses like aspheric lenses reduce image distortion and improve performance, essential for applications in AR, VR, and autonomous systems. The last one is advanced optical synthesis techniques. This modern method like fusion with for vision and reinforced optics enable the creation of high-quality complex components using deep mathematical techniques.
Next, we move on to future trends. The future trends for glass in the field of optics and imaging are being shaped by advancement in material science, nanotechnologies, and the growing demand for higher performance and sustainability. First, advancement in nanotechnologies. The use of nanotechnology in optical coating is an area of increasing interest and research. Nanotechnology allows the precise engineering of coating at the nanoscale, enabling control over optical properties with unparalleled precision. This level of control is opening up new possibilities for customized coating that can be tailored for specific applications, leading to improved optical performance and enhanced functionalities. Next, high-resolution imaging in medical and scientific field. Glass is playing a vital role in development of medical imaging systems such as endoscope, microscope, and optical coherence tomography (OCT) devices. The future of medical imaging will see more advanced glass-based optics for high-resolution imaging at the cellular or even subcellular level. Last but not least, advanced optical technologies (AOT). High-level research and development in photonic and optoelectronics is provided by the AOT department, implementing ideas to enable sub-lifetime light manipulation with the use of cutting-edge nanotechnologies. Among the efforts are integrated lasers, sensor, 2D optoelectronic, flat optic, and so on.
Lastly is the conclusion. Due to this unique combination of optical, mechanical, and chemical properties, glass has become an essential material in optics and imaging. Their extremely low level of distortion is critical to optical system performance, particularly in applications such as AR or VR devices, which is augmented reality or virtual reality devices, cameras, and medical instruments where lens quality significantly affects system performance. And glass lenses are susceptible to fragility and in-service breakage. Recent developments like specialty coatings and smart glass demonstrate ongoing innovation in glass manufacturing, ensuring that this material will continue to be crucial for many applications into the future. In response to this demand, higher performing optical systems will continue to be enabled with glass, laying the foundation for what is possible in imaging and optics, whether that be in support of science, technology, or even just day-to-day business.